Hello friends, welcome to today's episode of Problem of the Day series from the Leetcode. If you find this video to be helpful, we kindly ask that you consider liking this video and subscribing to our channel. Doing this will assist us in boosting the video's visibility through the YouTube algorithm. So let's get started. So today's problem is finding out the maximum width of a binary tree. The maximum width of a tree is the maximum width among all the levels. So, and let's try to understand that what is the width is. The width. So let's say this is the tree that we have. So in this particular tree, we have 1, 3, 5 and 3 and 2 and 9, right? So the thing that is mentioned is consider this is a complete binary tree. So when I say complete binary tree here means that this node 2 does not have the left child. So let's assume that it has a null child, right? And then the distance between the leftmost and the rightmost is what? So it's a number of nodes like 1, 2, 3 and 4. So that means the width of this tree is at this level is actually fourth, right? And at this level this is 2. Since have to find out the width at the level, so we might be considering using the breadth first search. Let's take another example. So here, this example, so in this case 2 does not have a null child, so assume that let's say it has a null child. Then this is having a null child, 5 having this null child, and assume that null also has the null child. Null, null, null and null. So in this case, now let's consider count the number of nodes. So you have 1, 2, 3, 4, 5, 6 and then 7. So this is the maximum depth, maximum width of 7 at this particular level. Alright. So let's try to understand how we are going to solve this. So if you notice that this is a complete binary tree. And in a complete binary tree, I have to find out the leftmost and the distance between the leftmost and the rightmost. So let's consider let's use the property of complete binary tree. So in a complete binary tree, you have every node have either 2 nodes or they will not be having any nodes. So this is a complete binary tree, right? And this, right? Uh, Now I have to find out the number of nodes between these. So at every level, the number of nodes gets multiplied. So it has a, like say 1 element, then it is 2, then it is 4, and this is say 7. In the last level it may be less than n. So we can leverage a property. Let's say if we do the numbering of nodes, so let's say number of this node is 0, then we can say that the left child is having the index of like say 0, and this will be 2 times this node plus 1, which is 1. Okay, now then after that for this node the left node will again be 0, and the right node is going to be 2 times this plus 1, so it will be 3. And similarly here it will be 0, and this will be 2 times 3 plus 1, which is equal to 7. This means that if while doing a level order traversal, if we consider if we also keep track of the position of the node we might be able to find out the distance between these two nodes. That means that the depth of this will be the position of this and the position of this. The difference between that, if we can find out, that will help us to find out the answer. I think that's good enough. Let's get started and code it. Let's validate the input. If root is equal to null, then return 0, right? And then we are going to do level order traversal, so we are going to create a queue, right? uh, as we discussed that while doing the level order traversal breadth-first search, we need to track the index or position of that particular node, right? So we can do either create a tuple, or we can also create a separate class data, and you can have public tree node, and I can say public integer index, right? So this will just help it will uh, be it will be just easier and more maintainable. So, and then create a constructor of this tree node and integer index, and node is equal to n comma index is equal to I. Okay, and now let's create a queue. Data queue is equal to new queue of data, and populate the queue by adding the first element, that is the root. Queue dot enqueue new data root, and let's start with its index is 0. Okay, now we will do a level order traversal like breadth-first search. While queue dot count is greater than 0, we'll keep on doing. Let's create a result max width, initialize with 0, and at the end we will return the max width. Okay, now uh, since we are going to do level order traversal, so we might also want to process the all the elements in the queue at any given moment. But since we keep on appending the items into the queue, so and the size will keeps on changing, so it might keep process everything in a single loop, which we don't want. So integer queue size is equal to queue dot count, and that process all the elements in the queue at this level. So I is equal to 0, I is less than uh, queue size plus I, right? And then take the element from the queue, and pull the node tree node n is equal to current dot node, and then process the left child and the right child. So if n dot left is not equal to null, then I am going to insert that value queue dot enqueue new data of n dot left, comma its index will be 2 times uh, the index of this parent, which is current dot index, right? And similarly we will process the right one, so n dot right, and right, and this will be plus 1, right. Okay, so now the thing is that once you're processing right in the queue, so the width of the at any level is the first element position and the last element in the position. So that means that we need to find out the first element and the last element. So let's do that. So before processing at any level, right? So let's say we say data, which is a start, which will be the first element in the queue. Which so queue dot peak. Okay, and then we also say what is my end is equal to null, and here we will update the end is equal to current. So at the end of this for loop, I have both start and end uh, evaluated. So now my max width is equal to math dot max width comma end dot index minus start dot index plus 1, and then we return max width. So okay, 37 line 37 and dot left. Okay, sounds great. Let's submit it, and succeeded, right. So now one follow-up question here could be that can we solve this problem using depth first search? BFS looks straight, it's quite intuitive, right? Can we do via the DFS? So let's try it. So in this particular way, right, let's evaluate how we are calculating. So at any point of time, right, at any given depth, what we are doing is, what we need is the minimum index and the maximum index that we have, right. So when we are doing a recursive at any given node, we can find out what is the depth of that particular tree. Okay, we know the index. So what we can do is that when we are implementing the depth first search, uh, we might want to store the index that we have seen at that particular node or particular depth actually. So that means that we can create a dictionary, right, and that dictionary contains, so at every depth like say 0 1 2, and we can have minimum and maximum stored, right. uh, then we can take the maximum minus minimum plus 1 to find out the maximum weight. Now the interesting part here could be that do we really need these two variables? Uh, if we consider that we what we really need is only one variable, so that when we are evaluating, so suppose that when it came here, right, so we calculated the first index is 0, right, the first column index, and whenever we get the new element, right, what we can do is we can calculate the maximum width at that time and update the result. So we can always, we just need the first index to store that. So we don't need to store this minimum and maximum, we can just store the index here. So let's say how we are going to code it. So let's remove it, the code. We'll remove this, and then We are going to remove this, and we might want to make it global, which is not bad, but I think solving the problem is much more important in interview than coding practice. Okay, so we have max width here. So what we are going to do is we are going to create a function, depth first search, and we are going to call root, and then we are going to what we need is the depth, which will be 0, and then the column index, which will be 0. Okay, and we need a dictionary, private dictionary of dictionary. And now let's implement the DFS. So private void DFS tree node integer depth, and then we are going to, integer index. Okay. DFS is going to be look simple, but let's simple first do a we are going to first visit on the left side and then right side. Okay, so now if root is equal to null, we are just going to return, and then we are going to process the left side and the right side. So DFS root dot left comma depth will be increased by 1, and the index will be 2 times star index, just like we did it on BFS. And then we are going to call DFS root dot right depth plus 1 to index plus 1. So this is similar to what we did on the BFS. Okay, now here comes the cream part, where we are going to calculate the maximum width. So if I have seen this particular depth, or I have not seen, so if I have not seen the depth, we'll just add this index in the dictionary. So if dictionary dot contains key, this will not. So we'll just add it here. Dictionary dot add depth index, right? And then if it is already present, so now calculate the maximum width. So max width is equal to math dot max of max width comma. So this index, if I already seen earlier, then that's the first one, otherwise it is the last one, right? So that means that this will be more than the previous entry in the dictionary. So this will be index minus dictionary of depth and plus 1, right? And that should be good enough. Run, submit. That works fine. Let's evaluate the time complexity. So in a DFS way, if we consider that every node is getting widgeted only once, right? And so the time complexity for this particular approach will be on, and I think it's for the BFS the time complexity will also be on, because we are widgeting node only once. Now comes to time complexity, space complexity. So in this case, we have dictionary, right? And this is the depth, so which is the depth of the tree. And in if your tree is ideally, it's a height of the tree. In worst case, where the tree is completely skewed, in that case the space complexity is going to be n, right? And so worst case space complexity for this approach is n. All right, so that's good for today. If you have found this video to be helpful, we kindly ask you that please consider liking it and subscribing to our channel. Doing so will assist us in boosting the video's visibility through the YouTube algorithm. Thanks for watching and see you tomorrow. Bye.